All right, thank you very much for the awesome introduction. It's wonderful to be here. Thank you for having me. Where are my slides? Oh, there we go. Right, so I'm here from Princeton. I run the Princeton Visual AI Lab. And what we focus on there is we're building building blocks of visual intelligence. So for example, things that can look at an image such as this one and figure out where all the objects are, figure out the more general scene understanding components, so the fact that it's a picture of a park, where are the buildings, where's the sky, or things like action recognition. So look at the people in this image or in a video and figure out what they're doing. So how do all of these building components get built? So here's the standard simple computer vision paradigm that's worked time and time again. So suppose you want to build something that can recognize all objects in an image. What do? You collect some training data. You get some images that come with some labels. In these pictures, there are cars. In these pictures, there are dogs. Now that you have this data, you focus most of your efforts on building the algorithm. So you build bigger, wider, deeper network these days. And this algorithm learns from the training data and given a new test image can output the list of objects. All right, so this is the standard AI vision system. And as I've said, has worked time and time and time again. If you look at any of the big success stories of computer vision, the fact that we're now sorting all of our mail using computer vision, 99.9999% of it. We have frontal face detection, all cameras. We deposit checks by taking a picture. We have systems that can drive around, read house numbers. All of these things were constructed using this supervised learning paradigm. So what's missing from this picture? So as I've mentioned, a lot of the time we focus our attention on building the algorithms and building bigger networks or building more complex systems. But I think there's a few things that are missing from this conversation that I want to talk about here today. So the first piece is that this training data doesn't drop in our lab. This training data doesn't come from somewhere, it doesn't just appear. There's usually a person or more likely a group of people that's labeling this data, whether it be annotating objects and images, whether it be annotating temporal extent of human actions if we're talking about video understanding. And this is important to realize for two reasons. So first, data sets drive computer vision progress. And these are some of the now historic data sets, so Caltech going to Pascal, going to ImageNet. There's many, many other newer ones these days. As the data set scale and complexity increases, that forces computer vision capacity to go up. For every data set, there's many, many, many algorithms that are being developed on this data set. The data sets allow the algorithms to both learn from progressively more complex data, as well as benchmark more and more complex tasks. Besides the fact that data sets drive computer vision progress, there's also a lot of very interesting questions, very interesting research questions that come out of this in the human-computer interaction space, questions around how to do efficient crowdsourcing, questions around how to actually harness human knowledge effectively to train these AI models. So let me tell you a couple of examples of this. So here's one example. Suppose you want to do the problem of multi-label annotation. You have a list of images. You want to label what objects are in there. And it's just a binary annotation question for every image. Is this object in there or not? Why is this important? Well, this is important for building object detection benchmarks if you want images where all of the objects in there are annotated so you can build object detection systems. But this is actually a general problem. It applies to annotating musical attributes of songs or actions in movies or sentiments in documents and so forth. Suppose you're thinking about this on a fairly large scale. So you have about 120,000 images, you have 200 objects. So this comes out to 24 million human questions. Back of the envelope calculations, this is about 6 years of human annotation time. Even if you parallelize it, that's a long time. And more importantly, that's a lot of money to pay for annotation, particularly, again, if you're doing this in academia. So one of the key insights you can notice here is actually these questions are not isolated questions. There's some structure in the question space. In particular, if you're trying to annotate whether the image contains cats and dogs, what you can, instead of asking about each question individually, you can ask a more general question of, does this image contain animals? And if the answer is no, sort of for the price of one question, you actually immediately know that the answer to dogs and cats question is no. And so this idea of building a semantic hierarchy along with some other optimization, sort of smart selection of which questions to ask next when doing this kind of annotation, leads to two results. One is it allows a 6x saving in multi-label annotation costs, which again is a general result published in a human-computer interaction conference for doing multi-label annotation. And the other outcome of this is this allows us to construct the ImageNet object detection benchmark, which scales up previous efforts by an order of magnitude number of images, an order of magnitude and number of objects, and allows the computer vision community to now work on large-scale object understanding, to work on building systems that are able to understand more and more and more objects in the world. Let's talk about another example. Here, suppose you're actually working within some budget constraints. So it's not that you're trying to minimize the amount of annotation in a task. Suppose you have a fixed amount of human annotation budget, and you're trying to build a system that's able to do a complex task. In this case, consider the task of semantic segmentation. This is the task of, for every pixel in the image, you want to assign a label to it. So there's some number of objects that you want to annotate and that you want to recognize. And you want to actually be able to build an AI system that can outline these objects. So here's your training annotation options. So you could go the very expensive route. You could go the fully supervised, fully annotated route, so where you get humans to, during training time, actually outline the objects. On the other hand, you can go the simpler route. You can do image level annotation, where you just get humans to tell you what objects are in there, whether they're present or not, without doing any supervision at the pixel level. So this will be much cheaper, but this allows you to collect many more images, annotate many more images. There is a middle ground that we propose, which is when you look at an image, don't just say whether there's an object, yes or no, but if the object is present, you point to it. You just click once on this object. So you essentially annotate one pixel. There's all these options. How do you actually trade off between them? Which ones are actually more or less effective for doing semantic segmentation within some budget constraints? Well, so you need to build a model that is able to learn from this. So you can build a CNN. This is a fully convolutional network where it outputs predictions at every pixel what object is in there. And during training time, you can supervise it with one pixel or a set of pixel or image level labels. If you just have one pixel, then essentially your loss function just propagates from that one pixel and just enforces that at training time, this network must produce the correct label at that one pixel. But you can train this or in a standard supervised way where you have labels for everything. So now that you have the system, you can actually look at how well does it perform with these different levels of supervision. So again, if you do full supervision, you can annotate very few images because it's very expensive to annotate. But you can annotate, in this case, 800 or something images. You can train the network with it, you get some result. If you go to image level labels, you can annotate many, many more images. Because there's many, many more images, there's more variety in the data. You see, oh, actually, the trade-offs work out such that it's actually more effective in this budget constraint to annotate images with image level labels. And as it turns out, if you do point level labels, you annotate slightly fewer images because it's slightly more expensive than just doing this binary labeling, but it actually is much more effective for training the network. So your test time accuracy of the network actually goes up significantly. So this is just a couple of examples that I talked about of why it's important to actually consider how this human knowledge gets shared with AI. What are the most effective ways to get humans to teach AI systems, to teach visual AI systems, teach computer vision systems about the world. And just working on algorithms alone in isolation may not quite be the optimal strategy. You actually want to consider where this data comes from and what is the right way, what is the best way to get this data. So this is one part of the story that I think is often missing. Here's another part, and this part will be very quick. This is just one slide. So it is, again, not enough to just consider the algorithm, just consider the network being built. We actually have to think about ways in which this algorithm will interact with humans. So why do we need human-in-the-loop AI? Why is this important? So there's three reasons. Possibly this is the simplest one. Is just that a lot of the time in developing the system, we don't actually know what it has to do, what the final user is going to want to do. So for example, if you're building a system that can retrieve images for you for a certain concept. Sometimes maybe you want human feedback at test time. It's important to be able to incorporate that alongside with your model. The second reason, possibly a little bit going one level deeper, is that datasets actually can't foresee all scenarios. So there will inevitably be things that you encountered that wasn't present at training time. And this is true for us as well. As we go around the world, we often encounter scenarios that we haven't seen before. And what we end up doing is asking our friends for help a lot of the time, asking nearby people to help. Oh, I haven't been in this situation before. Where is this and this? And the third reason, so datasets can't foresee all the scenarios, but also, even if they could, algorithms are inherently imperfect. And that, again, we are imperfect, AI is imperfect. If we wait to deploy these models in the real world until they're perfect, until they have 100% accuracy, that's not going to work. That's a really bad idea. And I also argue that that's actually never going to be the case. But what AI models now are really good at is analyzing large collections of images, text, large amounts of data, and sort of picking out key things. So for example, the application of video surveillance. So AI models are really good at looking through large collections of video and sort of picking out key parts that a human can focus on. So I'm not going to go into talking about this human-in-the-loop AI research in the interest of time, because I want to get to the third part of this. But it leads into many sort of thinking about this leads to many interesting questions around building collaborative and, more importantly, transparent and interpretable AI. Because it turns out if you have an AI system that produces some output that makes no sense to a human, so an AI system that, for example, looks at a picture of me and says, oh, that's a cat, humans will immediately lose trust in this system. And as soon as that happens, as soon as humans can't understand what is actually going on with the AI system and why is it making this prediction that's perhaps is wrong, but what's worse, it's not just it's wrong, but it's wrong in a way that doesn't make any sense to humans, trust breaks down, and this kind of collaborative work becomes impossible. Great. So let me now switch and talk about the third part of this, the last part of this, which is ask you this question of who is actually building AI systems today. In particular, who is deciding where this data comes from? So for example, you can think about this. So if you're trying to build, let's say, a system that goes out into schools, you have a camera that you put in different schools that looks at the classroom and perhaps learns something about the way students are learning. Perhaps you're doing this to improve education in the school. Where are you going to go? If you're trying to build this, chances are you're going to go to the school that you went to. That's sort of the most natural thing. You go, you already know the teachers there. You can go and kind of start this conversation with them, collect the data from there. What that means that a lot of the time, data comes from data sources that make sense to us as AI technologists. We're building it. We're going to pull data from sources that we know about or that we're familiar with. Similarly, who is even deciding what problems to work on? So who decides that here are the important things to tackle? Maybe it's education, maybe it's medicine. Chances are actually, a lot of us, when we say we're working on a particular problem, there's a personal story behind it. There's a reason why we chose to work on this problem. And this is actually in some ways a good thing, because when we're deciding what solutions to explore, it actually helps to be intricately familiar with this problem. So if we're building AI systems for accessibility, for example, if we're building computer vision systems that help people who can't see very well navigate the world, it actually helps to be intricately familiar with this problem in even considering what solutions to explore. We know that AI will change the world. It is changing the world already. And the question is, who will change AI? Who will be building these systems? So this is the sad part. There is very much a diversity crisis in AI on many different levels. Some examples is there's 13% of women currently holding engineering jobs. Among tenure-track engineering faculty, there's less than 3% African-American, less than 4% Hispanic. These are the groups that it's relatively easy to get statistics for. You can consider many different slices of the population, and for many of those, we don't have statistics, again, because partially we're not even tracking this, but just looking around this room, you can actually start thinking about how homogeneous we are as AI technologists. So these statistics are about engineering as a whole. So what makes AI in particular special, even more special, I would argue, even more in crisis than the rest of engineering? So first of all, I've kind of alluded to this as well. So AI is a rapidly growing, revolutionary, and application-focused field. So we work very closely with developing final applications. And so in this, it's actually critical to avoid bias to particular demographics, needs, and values, which inevitably happens if we're a homogeneous population building these tools. Second, there's a fear around AI that doesn't exist around the rest of engineering, or at least doesn't exist as much around the rest of engineering. AI is potentially more dangerous than nukes. The development of AI could spell the end of the human race. What this fear does is when there are folks who don't necessarily see themselves building AI, so when you're part of a group where you don't see yourself represented in AI, you don't have mentors and role models in AI, you don't really feel like this is a field for you, and compounded that with the fear, why would you want to work on a field that's going to spell the end of the human race or take away our jobs? If you don't see the positive benefits of AI, if you focus on this fear, why would you even want to bother trying to break into this field? And the third reason is there's actually even, again, it's very hard to collect statistics for this, but it's actually, there's even more of a diversity crisis in AI than the rest of engineering. So as one data point at Stanford, women now account for 32% of computer science majors, which is actually very good for computer science, but it's still only 15% of the AI specialization. And there's other statistics as well, like NIPS, for example, is 13% women and has been for many years. So with this, AI for All is a foundation that I co-founded last year. The AI for All's mission is to increase diversity and inclusion in AI education, research, development, and policy. And one of the most inspiring quotes, one of the biggest sort of claims to success of AI for All is this quote from AI for All 2016 student who says, "Until this program, I never thought that people who look like me could succeed in computer science and AI." And what we do at AI for All is try to address all of these things, both kind of exposing students from diverse populations to AI, but also dispelling some of this fear and teaching them about all the good, all the wonderful things that AI can do for our world, other than take away all of our jobs and kill us all. So the AI for All model consists of three things. We're educating the next generation of leaders through summer programs in partnership with universities. These are usually programs somewhere between 1 and 3 weeks. We then support the summer program alums through ongoing education, mentorship, and career opportunities, because a 1 to 3 week program is just not enough. We want to keep these students engaged. And the third thing, we're actually expanding awareness by funding the alumni ambassadors of these programs to educate the broader community. So again, with these summer programs, we can only run so many of them, and at a particular university, you want to keep the program fairly small, so it's usually 20, 30, 40 kids. But that's not scalable, but what is scalable is we can get them to go out in their communities and start workshops for younger students, for example, kind of spreading this message of AI for social good and teaching some of the technical components of AI as well. So the AI for All team consists of, it's really the powerhouse behind this whole operation is Tess Posner, who's our awesome executive director. She's supported by 2 other full-time folks, so Nicole and Wells, who are the project marketing manager and the education manager. So the 3 of them are full-time employees of AI for All, and they're really the ones doing all the groundwork. There is a board. I'm one of the board members, along with Fei-Fei Li, with Rick Summer, and with Rab Govel. There's now a 5th board member as well, but that hasn't been publicly announced, so stay tuned. The AI for All is funded currently by some wonderful seed funders, namely Melinda Gates and Jensen and Lori Kwong. They are the ones who actually made this happen, that are allowed us to hire these people. They allowed us to actually do some of this alumni support and all of the other things that we're doing. So I already put up one quote, but in quantitative results, some of the results from the Stanford program that's been running since 2015. It's used to be called Sailors. It's now Stanford AI for All. Look at, so 83% of students are proud of what they built during the program. 75% of students feel confident that they can undertake a similar project in the future. And after the program, students are 20% more likely to feel like they're part of a community in computer science. And I should say this program targets girls who are rising 10th graders. They just finished 9th grade, they're going into 10th grade. So all of the students are girls. So this is 9th grade girls saying this. In 2018, we're going to be partnering with 6 universities. So as I mentioned, Stanford is running since 2015. Berkeley is running since 2017. So Berkeley targets a different population. So they're going after local low-income students. Princeton, we're starting in 2018. That is going to be a program for racial minorities. It's going to be rising 11th graders from groups that are traditionally underrepresented in AI, racial groups, so African American, Hispanic, Latino, and Native American. It's going to be co-ed boys and girls. I should mention, so each of these programs is unique. So AI for All develops, sort of helps with curriculum development a little bit, but really each of these programs is unique to the university. So the Stanford program, for example, has a lot of robotics, has a lot of very cool robotics demos, and has a lot of research projects that these girls are working on that are specific to the kind of work that happens at Stanford. At Princeton, for example, so Princeton is actually located close to Washington, D.C., and we have very close ties to AI policy there. So in particular, my co-director, so the Princeton program is co-directed by myself and Ed Felton. Ed Felton is my colleague in the Princeton Computer Science Department, but he is also a world leader in AI policy. So he worked at the White House for 2 years working on AI policy. And so we're actually going to take these students and take them on a field trip to D.C. And besides learning about AI technology, they also get to learn a little bit about AI policy. Some of the other programs, so Carnegie Mellon, Boston University, Simon Fraser University, are also going to be unique in their own ways. Some of them are targeting rural students. Some are targeting girls, again. Some are targeting, again, different underrepresented groups. So with that, I will conclude. So we've mentioned a few things, so namely 3 ways in which I think humans are sometimes left out of the conversation about computer vision when we just focus on building bigger and better models. We don't think about this bigger picture. We don't necessarily think about sharing human knowledge with AI and how this data comes into being and what are some of the interesting questions around that. What is the most effective ways to share human knowledge with AI, particularly as we move to more and more complex tasks. This will become more and more important. We often don't think about transparency and interpretability in AI, which is particularly important because ultimately all of these systems are almost inevitably going to have to be collaborative with humans. And the third piece is we oftentimes don't think about the dangers of building AI in a homogeneous population without actually having voices from everybody, from everybody who's going to be affected by this technology involved in building it. With that, thank you for having me. It's been a pleasure.
Thanks, Olga, for a super inspiring talk. So we have a few minutes for questions. Olga will also be on the panel, but please, your chance now. Please hold your hand up very high. There's a few.
Hi, Olga. Great talk. I'm going to ask you about the one slide that was all by itself, though. I'm a little worried when you said that you wanted to help make people trust AI, that was the reason that you wanted it to be interpretable. But it doesn't seem to me like trust is the right metaphor. We want people to understand it's a machine, not a person, right? So maybe attack the cat-person problem with using that to see that it's a machine and that it's not another person. Is that coherent? We're both jet lagged, so.
That makes sense. I mean, there's so I agree with you that trust can have sort of many different meanings. So what I was getting at is if you're building a collaborative system, so if you're having AI operate alongside a human, regardless of whether you see it as another human or as a system. So I was actually not even trying to get into that territory. But if you're working in collaboration, so with AI. So suppose you have a robot that's helping you clean your house, and you're kind of collaborating with it. You want to be able to trust it within the scope of this task that you're working on. So you want to be able to build an effective collaboration. And in order to build this effective collaboration, you need to have some, maybe trust is, I'm trying to come up with a different word rather than trust, but you need to have some, I'm gonna say belief, that the system will sort of do something that makes sense to you, such that you can work effectively together. So if we're going into this interpretability thing, I mean, you know that I'm very interested in the question of fairness and bias in AI, and I specifically didn't get to this here because this is kind of preliminary work. I'm just starting to work on this. But this question of interpretability, of course, also comes up when you start thinking about what kind of biases are encoded in AI, and think about doing fairness and bias in machine learning. Think about that research, and the question of interpretability is sort of front and center to that as well.
Hi, thanks for your talk first. So I was wondering, of course, when you mention all this, like the effort towards having equity at multiple levels, like race and gender, of course, I think this is super important in general. But I was wondering, when you mention this about people, like including everyone so that they may use this technology in an appropriate way, I was wondering what sort of problems you think of when this is not met. So if you don't include Hispanics or in the development of AI, what are the risks you are thinking of?
I think that it's hard to quantify these risks. It's hard to give, a particular, what, like, I think if I start trying to give a particular example of what happens when we don't include Hispanics in development of AI, I think we're going to go down a stereotyping route that I don't want to go down. What ends up happening is there is inherent bias that creeps into the system. For example, think about the example that I gave of schools. You're building, or hospitals. You're building computer vision systems that operate in a certain environment that you've selected because this is familiar to you, and you're building systems that can operate there. If you're excluding, again, groups of people, you might not even realize that this technology is learning about a particular environment that's familiar to you, but that may be completely different than somebody else's world experience. So this question of, I mean, one answer to this is where does the data come from? If it comes from a world that's familiar to you, it may not even come from a world that's familiar to others. But the other real question is, again, so because we can't really know what challenges and experiences are faced by folks who are not like us, so by other people, and again, sort of the race question you ask is very difficult to answer, but you can think about like accessibility, for example. You can think about folks that have different kinds of disabilities that if we're trying to build AI technology that help them, maybe we're kind of aware of this problem, but we don't actually have an insider look at it, so we don't actually know what they need and how to build the technology in a way that's most effective. It's a good question, so it's a very difficult one to answer.
Thank you.